I introduce the first speaker of this morning session, Professor David Black from Edith Cowan University, from the Center for People, Place and Planet. And he will speak about remote environmental monitoring based on IoT with valuable research result done in the southwestern part of Australia, if I'm correct, in the middle of the rainforest from there. So I'm a little bit familiar. I'm cheating because I've been there. So we've been there together, and we were inspected these sites where this research was performed. Few of them, because Professor David will explain us the areas where the research is going to take place. But what I can say, it is an interesting approach, and I'm very curious to see the results of their teamwork, because it's not one person's work in behind, because the Center for People, Place and Planet acquired together a large number of researchers, a large number of community members, and what I like very much also, First Nation is involved in this project. Native Australians are involved, so they have an important role in this project. So, Professor David, you have the floor.
Thank you, Levi, and thank you to the organisers for the Smart Cities Conference and for the invitation to present here today. It's a wonderful opportunity, so thank you. A little bit about me to begin with. So I am an Associate Director for a strategic research centre called the Centre for People, Place and Planet at Edith Cowan University in Perth in Western Australia. A little bit about the centre. So as Levi mentioned, it's a transdisciplinary research centre. So it is built around having multiple disciplines come together to tackle some of the issues that we're facing, both within Western Australia, Australia, and globally as well. So we have researchers from arts and humanities, we have from business and law, from our West Australian Academy of Performing Arts, from science, and from education. And so, yes, we have that transdisciplinary research approach. So the centre, what it sets out to do is to co-design research and action with and influenced by Indigenous knowledge holders. And so today I'm going to take you on a bit of a journey through a couple of research projects that we're undertaking in Western Australia. And I just want to point out that those research projects are actually co-designed and co-led with Aboriginal colleagues. And so we also do transform human-environment relations through place-based research. So all our research it takes place on what we call country. And we recognise living systems where we have interdependencies and mutualities, and to strengthen governance and management for sustainability. And so we have 3 programs of research. The first one is food, earth and water resilience, and that's mainly where my work takes place. Our other programs of research include feminist, creative and place literacies for eco-social transformation, and transforming responses to global environment problems. Before I begin, I will apologise if I'm not communicating very clearly. So I only arrived yesterday, and after a 20-hour travel, and I think my brain is still trying to catch up with my body. So, but today I'm going to talk about smart living in remote places. So as you'll see in a minute, Australia and Western Australia cover very large areas, huge land masses. And a majority of that land mass is what we refer to as rural or regional. And there are not that many people that live there, but we need the information from those areas to help make land management decisions in those areas. So of course, smart living is data-driven decisions, so we need that data to be able to make those decisions. Of course, in urban environments, Internet of Things has been a great success, and a majority of probably 70% of IoT projects take place within an urban environment where you have the infrastructure to support those types of systems. But what about in remote areas? As I said, we need that information, we need data, but how do we actually set up systems where you don't have very good connectivity, the conditions are quite harsh for deploying equipment, etc. So I'm going to give a couple of case studies today about some projects that we've been working on and how we've used or implemented IoT systems to help us collect data in remote regions. So it matters in environmental monitoring. It matters for a whole number of reasons, as I said. But for acquiring data in particular. In those areas that I'm going to be talking about, we have a large agricultural sector. A lot of our wilderness or conservation areas also occur in these rural or regional areas as well. And then, of course, we need to be prepared for disasters, and in particular, you may be aware that Australia is prone to both fires and floods, and so we need the information to be able to act quickly, particularly in remote areas, particularly where we have our First Nations people, where they may not have the access to a lot of the infrastructure or health facilities, etc., that we enjoy in urban centres. So we need to have systems that enable us to be able to provide them with the care and access to resources that they need. As I said, the accessibility is poor in those areas, and a lot of the data or a lot of decision making is done without the knowledge or the data to be able to make informed decisions in those remote areas. And these are the areas that we actually particularly need it in Australia and in Western Australia. So what is the challenge with deploying remote IoT systems? You have sensor gateway connectivity. Again, we're talking vast distances, and so how do we connect sensors and multiple sensors to gateways that then can feed that information centrally? How do we connect our gateways to the cloud? And of course, we need connectivity to do that. Power management, again, we're in regional remote areas. We don't have access to power where we can just be able to plug them in. So we need to develop power systems that can power them remotely and for extended periods of time. We have very harsh environmental conditions. We typically have summers in the areas that I'm working with temperatures regularly above 40 degrees Celsius. Again, and then there can be saline conditions as well, so a lot of salt in the environment. They can be acidic. So we have quite harsh environmental conditions that can be harmful to sensors and equipment. Validating your data, the high cost of actually travelling into the field to collect data. So as I'll point out, both our field sites are 1,000 kilometre round trips. So you can't just go out and actually collect data on a regular basis. And there are limited real-time capabilities. So to give you some context about Western Australia, the land mass of Australia is about 7.7 million square kilometres. To give you some idea, this is the number of countries that can fit inside Australia. WA, which is where I'm from, is about a third of that. So Western Australia is 2.6 million square kilometres. So we have a large expansive area. As you see from the map, our urban area is that small white area down the bottom in Perth and Bunbury, and that's where most of our population in Western Australia is concentrated. And so the rest of Western Australia is considered rural or remote. And so this is the places where we're trying to conduct a lot of our research. So we're located hundreds to thousands of kilometres from other cities. So Perth is probably one of the most isolated capital cities in the world. Our next nearest capital city is 3,000 kilometres away. So to give you some sense. So when I say I travelled 20 hours to get here, it's not unusual for us to travel a long way to get anywhere. And one of the main issues is connectivity is patchy. So once you move out of that urban environment, being able to connect to mobile data systems or even satellite systems, it becomes difficult and quite patchy. I'm going to talk about two case studies. The first one's in a town called Perenjori. It's an agricultural town. It's situated about 350 kilometres northeast of Perth, and as I said, it's about 7 hours round trip driving to get out there. And then the second one, I'm going to be talking about where Levy has been, and this is the Walpole Wilderness area in the Great Southern area of Western Australia. Again, it's about 1,000 kilometre round trip to get to our study sites. The Walpole Wilderness area is an area where we have peatlands, so temperate peatlands, and our research is involved in trying to preserve or conserve these peatlands. So the first study was about imperengery, is a study that was called Transformational Aboriginal Agricultural Methods, or TAM. And this is where we partnered with Aboriginal knowledge holders and elders to actually help come up with a plan to try and control the flow of water across the landscape, which you'll see is a big problem in a minute. And as I said, 350 kilometres northeast of Perth, we're operating on 2 farms out here. To give you a sense, the annual rainfall in this region is probably 300 millimetres within a year, and the 2 farms get half of that. So probably about 150 millimetres a year. So a really very dry and harsh environment. And when they get rainfall, it happens very quickly. They get it in very large downpours, and it causes a lot of erosion issues, as you can see here. So what we get in the landscape is we get these big erosion gullies or erosion channels, and it just takes all the topsoil away. And this is a big problem for the farmers. And so we had our Aboriginal colleague come in who are connected to the land and both spiritually as well as physically. And so they're able to provide guidance and information about how we might implement these things called leaky weirs to actually control the flow of water across the landscape and try and prevent it from taking all the topsoil away and having water remain, as they refer to it, as on country. And then if we can slow that water down, we get vegetation growing and repairing a lot of these erosion channels. So our job was to actually provide some science behind these interventions. So our Aboriginal colleagues would build the leaky weirs, try and control the flow of water across the landscape, and we were tasked with trying to put some numbers behind, is it working and how successful has it been? So to do that, we had what we call 3 intervention sites. So there was 2 erosion channels on one farm, and then another single erosion channel on another farm that we used. At each of these sites, we set up 6 plots and we did soil analysis, etc. We also measured soil microbiome and did carbon gas flux measurements. But more importantly, we implemented an Internet of Things soil moisture network at each of the sites. And then we used drone survey to acquire information about biomass, etc. So these are the sites, and these are where we set up our different monitoring sites. And so the Internet of Things consisted of a LoRaWAN gateway. We had 1 on each farm. We had multi-depth soil moisture sensors, so up to 1 metre, and they are measuring, I think, at every 10 centimetres in the soil profile. And then to complement that, we had rainfall gauges and temperature and humidity sensors set up as well. And so at each of those 6 sites, or at each of those 6 plots, at each of our sites, so we had about 18 different sensor systems scattered over the 2 farms. As I said before, powering these systems is difficult. They're remote. There is no way to just plug into the electrical system. So we needed to set up a portable power system for them. And you can see in that image on the right is how we do that. The LoRaWAN gateway is actually just attached to a branch in a tree at a high point on the farm. And then we have a solar panel connected to a 100 milliamp hour lithium battery that has a regulator that can continually charge and power the gateway. And then the sensors just communicate to the gateway. And so this is some of the sensors we're using. We use the multi-depth sensors came from Sensorterra, and we also use rain gauges, temperature and humidity, and some soil moisture sensors from Sensimo. And we again they all were integrated together. What was it able to tell us? Basically, some insights were, particularly for the farmers, that the top 30 to 40 centimetres of the soil profile is completely dry. So trying to grow crops, wheat, or any annual crop is almost impossible in these systems. They do it, but it's very difficult for them because it doesn't retain moisture for very long. What this was able to tell us was that there is a lot of moisture actually deeper down in the profile. So if they were actually to plant more perennial type plants, etc., that can access that water, and which one of our farmers was actually doing, it has a great deal of benefit for that system and to improve soil health. What it also showed us, and you can see the red line, is the leaky weirs. After they were installed, it actually changed the soil moisture profile in those systems quite a bit. So that told us that those leaky weir systems were working. And these graphs can just show you as well that how the surface soils were responding to rainfall. So they respond very quickly in the top 10, 20, maybe 30 centimetres. It takes longer for the deeper soil moisture profiles to respond, but they do, and then those changes persist for longer. Okay, the second case study is actually on conserving temperate peatlands in an area called the Walpole Wilderness area of Western Australia. It's a very large project. We have up to 21 scientists working on this project from different discipline areas, and we work collaboratively with Aboriginal elders and different community organisations as well. It's quite unique. It's one of the only, well, very few wilderness areas actually declared in the Southern Hemisphere. As I said, it's about 500 kilometres southwest of Perth, and it's in a high rainfall zone of Western Australia. So these peatlands form in an area where we have about 800 millimetres of rainfall per year and very high humidity, so 70 to 80% humidity in those areas. So it's in the southwest, in the deep southwest of Western Australia. We have peatlands scattered throughout there. They're poorly mapped and they're poorly understood. One of the biggest problems we have for those peatlands is fire. So this is a fire that was started intentionally in April 2024. I can't remember the exact area that it burnt through, but each one of these plumes that you can see in this photo is actually a peatland that is on fire, and they will burn for months. It's almost impossible to put them out, and you can't even get access to most of them. So the amount of carbon that is being released is significant from these systems when they catch fire. One problem we have is that our conservation agency, our government agency, also use fire as a management tool. So they actually put fire through the forest to try and reduce fuel loads, but because of climate change, when they do this, a lot of the peats are now catching on fire. So we need information that can actually inform them about when the peats are vulnerable to catching fire. So that's where we came in. Again, we set up our IoT systems, very similar to the last case study I showed you. This was our first iteration of a power supply unit up in the top image. And again, we just have the LoRaWAN gateway attached to a tree. And then we have a lithium battery powered by a solar panel. And then we connect all our sensors to that. A couple of the issues we have both on the previous project and on this project is with the power supply units. Our first iteration, which is the one here, it got blown over in storms, etc. And actually, so our system stopped working after a while. So we have to go down and try and repair it. That's where we came up with a different design that's a bit more robust. Vegetation is obviously an issue in these peatlands. We have a lot of heath type vegetation. It's quite dense, so getting the sensors to communicate with the gateway is a bit of a problem. And what I didn't mention in the previous study, in the agricultural study, is that we have a lot of sheep and goats, and they love to actually eat cables and things like that. So we had a lot of our sensors that stopped working because the goats or the sheep had actually eaten the cables. So all that information we get fed into a things network, and then we're able to access the information remotely, so we can access it in Perth. And this is just some examples. This is all our sensors for temperature and humidity. an example of the soil moisture information that we can get. And this is just some rainfall data as well that we get in. And then this is from Sensor Terra, and I'll talk a little bit about that in a moment, but this is the soil moisture graphs that we can see, and we can monitor how they're changing in the soil profile. And this is just some examples of all scientists out in the field, in the wilderness area, working on peats, etc. We have very rare flora and fauna in these areas. Rare frogs and lots of rare plants as well. So it's very important that we conserve these areas. So what are our key learnings? A lot of the barriers, connectivity is an issue. So in both locations, we're operating on 1 bar of 4G signal. So we're relying on that to be able to communicate all our data from those areas. In the peatland areas, there are some areas where we cannot get any connectivity at all. So we have to place the gateway where we can get connectivity, and then hopefully the sensors can communicate that distance to that gateway. So it is a problem. The other option is to use something like Starlink, but that becomes very expensive. Power I've already talked about. The resilience of the hardware and being able to be left out in remote locations for a long period of time. And most of the sensors that we've used and the gateways have been able to remain operating in those conditions as well. Different pressures for agriculture. We have a large spatial footprint, long sensor chain. So we're trying to communicate from sensors over a long spatial area. It's easier in agricultural areas because you don't have a lot of vegetation or infrastructure that will block the signal. In the conservation areas we do, so sometimes connectivity between sensors and gateway is a problem. The other thing is sensitive environment. So we don't want to be going into those conservation areas all the time because I said we have rare flora and fauna species. We want to keep our impact quite low. The benefits of having these systems, we get early alerts, we get information, we can use that information about the peats to inform the land use managers of when to put fire through the areas or when not to. Reduces our travel costs, obviously, and it's safer for us to be operating in those systems. Those systems themselves need to be quite simple. We try and keep them as simple as possible. The more complex they become, the more difficulties and issues that you face. They need to be robust. Okay, and then if we were to design a system for IoT for remote work, assess the environment. So you need to design a system that's suited to the particular climate and terrain that you're working in, and also for accessibility, etc. Choose the appropriate connectivity. In our case, it's LoRaWAN, but in other systems, there may be different connectivity approaches that are better. Resilience, actually build resilience into your system, and not only through the hardware and software, but also have some redundancy in the system as well. We have lost quite a bit of data where we've lost connectivity. So we actually have static loggers out as well, so that when the system falls over for whatever reason, we can continue to collect data during those times. And the final one is data sharing. So I showed you before, this type of system, this Things network, and we use Grafana to develop our platform, is great for us in being able to monitor the system. It's not very user-friendly for third parties, such as farmers or for government agencies. So our issue at the moment is developing a system, a dashboard system that is user-friendly, so they can have, it has more data analytics built into it, so they can actually access information like those graphs I was showing you before between rainfall and soil moisture levels, etc. That's it, I think. Thank you very much.